Hello, I'm Sihang Liu from the University of Virginia. This talk is an overview of PMTest, a fast and flexible testing framework for persistent memory programs. I will start with the background on persistent memory. This image shows Intel's recently released DC persistent memory module. The new persistent memory is high-speed, persistent, and bi-addressable. Using persistent memory, the program can directly manage persistent data in memory without going through the file system. And next I will talk about how to integrate persistent memory in the system. Conventionally, the program needs to go through file systems to access persistent data, typically stored on hard drives. And the file system guarantees crash consistency. In other words, if there's a failure, the file system will guarantee data's recoverability. With persistent memory, programs now has the ability to access memory directly without going through the file system. But we still need to have data to be recoverable, so that the program needs to guarantee crash consistency. There are two fundamental guarantees for programs to ensure crash consistency. The first guarantee is durability guarantee, that is, write can become persistent in memory on demand. In this example, the processor is volatile and the memory is persistent. So the program needs to issue a flush instruction so that it can write back the data to persistent memory and make it durable. And the second guarantee is ordering, that is, one write becomes persistent in persistent memory before another. In this example, if there are two cache lines, the first one needs to be written back. After it's persisted, the second one can be written back. The hardware platforms provide low-level primitives for crash consistency. For example, x86 and ARM platforms all have their instructions to guarantee durability and ordering. And academic proposals are also satisfying these requirements and further improve the performance. Let's take a look at how to use the low-level primitives. The example is a function that appends a node to a linked list in persistent memory. So first, the program creates a new node, and second, it updates the new node's next pointer, and third, it updates the head pointer. And finally, use a persist barrier to ensure updates has been persisted. The example seems correct, but lines 3 and line 4 can be reordered. So if the head becomes persisted, but the new node has not, then if failure happens at this place, the new node could be lost, and consequently the entire linked list is lost because the head is pointing to a non-existing piece of memory. So to fix this problem, we need to insert a persist barrier in the middle, and since data has been persisted, we can always have a consistent linked list. So we conclude that ensuring crash consistency with low-level primitives is hard. To make it easier to implement those persistent memory programs, there have been libraries that are built on top of the low-level primitives, such as Intel's PMDK, and there are other many academic proposals. And now let's go back to look at the same example, but implemented based on the transaction. The transaction from PMDK provides interface like txBegin and txEnd that wraps the whole procedure, and use txadd to make a snapshot or a backup of the data that is going to be updated. So first we still create a new node, and then before we update the head, we make a backup. And finally, we increment the length. The example seems correct, but still there's a mistake. The length is not backed up before update. So if there's a failure, the linked list could have inconsistent length. To fix it, we need to insert another txadd before incrementing the length. So now this is a crash consistent program. We conclude that ensuring crash consistency with transaction is also hard, because the program still to know the behavior of the program and also understand the persistency guarantees from the libraries. Now that we have seen that it is hard to implement a crash consistent program, but testing is also not easy. The writes can reorder during runtime. For example, given a simple trace of write A, B, and C, there could be many reorderings. And the reordering is happening in the hardware, which is invisible to the programmers. Therefore, it is hard to determine whether the program can lead to an incorrect runtime reordering. So it would be good if there's a tool that can help programmers assert on the ordering and persistence, such as if A has been persisted or if A has been persisted before B. To solve this problem, we developed a testing tool, PMTest. PMTest first target expert programmers who tend to implement things such as libraries, highly optimized low-level programs. So we provide a searching-like low-level interface to check if the behavior meets the specification. We also target normal programmers who tend to use high-level interface such as transactions. PMTest can automatically inject low-level checkers to those transactions so that it can minimize programmers' effort. The low-level interface includes two low-level checkers. First one is ordered before, and the other one is persisted. These checkers correspond to the two fundamental guarantees of persistence. At runtime, PMTest collects the trace from the program and sends it to a testing engine. The testing engine detects whether there's any violation against programmer-specified ordering and durability requirements. And in this example, because there's no write back and fence between A and B, the output is A may not persist before B. The high-level interface is simpler. It automatically injects low-level checkers to PMDK transactions. In this example, we first check whether there's any missing backup before the update, and also make sure that all updates has been persisted in the end of the transaction. PMTest is a very flexible tool. It supports different types of software systems, including kernel modules, persistent memory libraries, and custom programs built on top of the libraries. On the hardware side, it not only supports existing hardware, but also can be extended to support academic proposals. PMTest is also fast. When testing micro-benchmarks from the PMDK library, PMTest is 7 times faster than Intel's testing tool, PMCheck. And when testing real-world workloads, the performance overhead from PMTest is less than 2x. So we conclude that PMTest is not only flexible, but also fast. We have detected new bugs in PMFS and PMDK applications using PMTest, and this tool is open sourced as the following link. Finally, I'd like to summarize this work. The new persistent memory allows direct management of persistent data in memory. However, it is hard to guarantee crash consistency. So we developed PMTest, a tool that detects such crash consistency bugs. PMTest is not only fast, but also flexible. It supports different types of software systems, and it can be extended to support future persistent memory hardware platforms. It only introduces less than 2x overhead in real-world applications. PMTest has opened up new directions in testing persistent memory programs, such as runtime testing, test case generation, verification, etc. We are glad to see follow-up works from recent venues that take these directions. Thank you.